All right, let's take a look at our first lesson for today. So we're going to look at exponential functions. So first of all, let's remind ourselves, what is an exponential function? So these are functions where there is the variable is the exponent. That's what an exponential function is. So for example, this is 1, like 2 to the x, that's an exponential function. Also, let's say e to the x. Those are both exponential functions because the variable is in the exponent, the x. So for a general form of an exponential function, this is the general form where you have just a number c, and then a is the base to the x. So for example, perhaps we have 2 times 3 to the x. According to order of operations, we would deal with this portion first, the 3 to the x, and then we would multiply by the 2, if you recall. So that's a general form of an exponential function. This formula right here, this is just a kind of a fun, fun thing. We're not going to really do any work with it or much work with it this year. This is something that it's a concept that we're going to cover in calculus. But E, which is, you may be familiar with E. We used some E's last year. E is the Euler number. And this is a concept that we will use in calculus. So we're just looking at the relationship between what we're doing now and what we will be doing. So the Euler number is that limit. Limit as n goes to infinity of that 1 plus 1 over n to the n. And this is actually the Euler number. Of course, it keeps going, just like, pi just keeps going and going and going. So does the Euler number. It just keeps going, going, going. It's just a number. So now let's review our exponent laws. These exponent laws are like so important to our work in every kind of math, in algebra, in trig, in calculus. It's so important. So just a reminder, when we have the same bases, we're multiplying with the same bases, we would add the exponents. Okay, that's like the law. We would add the exponents. When we are dividing, we've got the same base, we're dividing, we subtract the exponents. This should be just a review for you. So this is review. When we have two, so notice that these are connected by multiplication. When they're connected by multiplication, then what we do is we distribute the exponent to each entity of the multiplication. If they're connected by addition, this is a no-go. This is not possible. We've talked about that numerous times, right? Numerous times. For example, if it was like, a plus b to the x, like that. This, doing that business is not a thing. Okay, that is not a thing over a plus. We don't do that. Ever. Okay, that involves, we've dealt with this quite a bit before. So, no distributing over pluses or minuses. So, likewise, when we have, where two bases or they're being divided to the x, we can, it's kind of like distributing each of them to, so that we can work with them a little bit easier, so breaking them up into pieces. This is a reminder of this portion right here is how do we switch between exponential and radical form. So this is how we change. This is how we change between exponential and radical form. how we change. So, for example, let's say we have, these are just exponent rules, by the way. So let's say we have x to the 2/3. Okay, if we were going to rewrite that, that's called exponential form. The first thing I just wrote, this is called exponential form. This is going to be the same as the cubed root of x squared. So I'm going between exponents and radicals. Okay, so that should be a review. One other thing that I want to note is that anything to the 0 power, any object to the 0 power, of course except 0, because it tells you it can't be 0, is 1. For example, you know, e to the 0 is 1. It just is. Anything to the 0 is 1. Now that takes us to these other properties or laws over here on the right. These have to do more with how we solve. So if we look at this, if I have two exponentials with the same bases that are equal to each other, then I can basically, I'm not going to say cross the bases out, but it's as if I just ignore them and I set the exponents equal to each other. That's how we solve exponential equations, if you recall that. Remember? We just kind of ignore the bases and set the exponents equal to each other. It works the other way also. If our exponents are exactly the same, that means that our bases have to be exactly the same. We really don't use this number 7 very often, but it is a law that's handy to know. Okay, on number 4, these are, I call power to power. Power to power is where we multiply. Power to power means multiply. It means multiply our exponents. Okay, so power to power is multiply. This one over here, number 1, base times base. So some teachers say base, base, add. I don't know if that little saying will help you. When you're multiplying bases together, base times a base, and they're the same, you add, base, base, add. You add the exponents. Maybe that will help you memorize it. I'm not sure. Okay, and then the last one, if you recall, when we have negative exponents, we can rewrite the negative exponent. So this, a to the negative x, is the same thing as 1 over a to the x, our negative exponents. For example, if we have, let's say, 5 to the negative x, that's going to be the same thing as 1 over 5 to the x. It works the other way also. If we have, say, 1 over 3 to the negative x, that's going to be the same thing as 3 to the x. It goes both ways. Now again, if there's any pluses and minuses hanging on, we're done. We can't do this. We have to do something different. All right, so that is a reminder of our exponent laws. So let's go to some examples. This is similar to the kind of homework you're going to have. So they're going to give us a table like this, and they're going to ask us linear, exponential, or neither. But in order to answer these questions, we need to know some information, right? What things do we need to know? So I want to put them as notes down here. So if the average rate of change is constant, the function is linear. We know the average rate of change is slope, right? It's the slope. So if the slope So if we look at this first one, we've got an average rate of change. How do we calculate it? We do that formula f of b minus f of a over b minus a. It's just change in y over change in x. Notice how those changes are all the same. So this one, because of that, this one is going to be linear. Okay, our second note that we need to know is if the ratio of consecutive outputs, if the ratio of consecutive outputs is constant, the function is exponential. So this is how we tell. So we look at this one, and what they're doing is they are taking these values right here, and they're putting them in a ratio. Like 16 over 32 is a half, 8 over 16 is a half, 4 over 8 is a half. And all those ratios end up being the exact same thing. That means that this is exponential. So really, to be able to answer a question like that, you just need to know this information down here. If you know this information, you can answer any of those questions. If you don't know that information, you're not going to be able to answer the question, unless you do a lot more digging around. Okay, we okay so far? All right, so the next thing we're going to do is we're going to do some solving. Again, we did this last year. We want to, I like to write steps out. You know how I really like steps. So let's write down steps for solving. So here's our steps. Okay, so step number 1, make the bases the same. Make bases the same by rewriting. We're not multiplying by anything, ladies. We're not doing anything like that. We're rewriting it. And then the second thing we will do, once that's done, we set the exponents equal to each other. We set exponents equal. Then we solve. And that's our technique. I mean, that's what we do. Those are our steps. So we make the bases the same by rewriting each base. Then we set the exponents equal to each other and solve. Okay, so what do we mean by rewriting? Well, an example of rewriting. So let's say, I don't know, let's say I've got 64. How could I rewrite 64? 64 could be written as 8 squared. Right, that's okay. We can rewrite like that. We could even go smaller than 8 squared, right? Because if we were looking at a, well, let's see if we can. So if we're looking at a factor tree, so I got 64, I've got 8 times 8, 4 times 2, and 2 times 2. So I've got 1, 2, 3, 4, 5. I've got 6 2's. So I could also write it as 2 to the 6. Those all mean 64. So when I'm rewriting, I'm just changing the way it looks. I'm not actually multiplying by anything. I'm not doing anything except rewriting. Okay, and we would rewrite it to our advantage, whatever our advantage is. Okay, so if we look at number 2, and we're going to rewrite the bigger one, the 8, right? I could rewrite 8 as 4. No, I can't rewrite it as 4 squared. That's 16. So what can I rewrite as? I can rewrite it as 2 cubed, right? 8 is 2 cubed. So let's rewrite. So I'm going to rewrite 8 as 2 cubed. Okay, notice I just opened up where the 8 is and I put its rewrite in there. The rewrite is for 8 is 2 cubed. And I really want my bases to be the same, so I have to ask, so I start with the bigger one, just try to get a feel for it. You don't have to, you can start with a smaller one, it doesn't matter. 4, could I get 4 as a base 2? Yeah, I can, right? 2 squared. So I'm going to rewrite 4. I'm going to rewrite that as 2 squared. So now I have my rewriting done. Step 1 is done. Step 2 is set the exponents equal to each other and then solve. So the exponents are these parts right here. Right, those are my exponent parts. So I've got 2 times 2x minus 1 equals 3 times x. That's what I need to solve. Okay, so let's do our solving. We've been solving for a long time, ladies, right? We know how to solve equations. So that would be 4x minus 2 equals 3x. I would move the 3 to the left. That would give me x is 2. Okay. The next one, that's a bunch of crazy looking stuff down there. If you look at them, they all have a version. If we look, they've all got somewhere base e. They're all like have base e's. So there's got to be something I can do to work on that. So on the left side, I have e to something, so I'm happy with that. But on the right side, I have this kind of combination of things going on. Again, what do I want? I want e to something equals e to something. I mean, that's what I want, right? I want the bases to be the same so I can ignore them and set the exponents equal to each other. That's my goal. Right now, I've got a couple of different e things going on here, and it's not going to work. So let's work on cleaning this up a bit. The first thing that I would do is I would take this and I would make it a whole, look like a whole number. I'd pull the e cubed up to the top. So that's the first thing I would do. So e to the negative x squared equals e, and let's see, x times 2 is 2x, e to the 2x times, and I'm going to rewrite that to be e to the negative 3. Okay, so that's my first step, is I want them to be all level, all the same level. I don't want some to be in the denominator, some to be in the numerator. That's not helpful. So now I've got the base add scenario going on, right? Those on the right, those base e's are the same. So I've got e to the negative x squared equals, so base add. So when I multiply those two same bases together, I add their exponents, or in this case, subtract them. So now I've got my bases the same. So I've done step 1, make the bases the same by rewriting. That's what we did. Number 2, set the exponents equal to each other, then solve. All right, so let's ignore the bases. So I got negative x squared equals 2x minus 3. Now we've got a quadratic going on there, and I really don't like factoring leading coefficients that are negative. So I actually would move the x squared to the right side. That's what I would do. You certainly don't have to. You can do whichever way you want. But I don't like factoring leading coefficients that are negative. So I'm going to move this over here. So that gives me x squared plus 2x minus 3 is 0. Hopefully that's factorable, because if it's not, I'm going to have to do like quadratic formula. Okay, so x and x, the back sign is negative, so we've got a negative positive. Looks like we've got a 3 and a 1. Okay, so we've got x is negative 3 and x is 1. And that's our little reminiscent of solving equations, exponential equations. How we doing? Okay, so graphing. Let's look at graphing. That's our last problem for today. So we're doing a little bit of different kind of things. So when we graph exponentials, I'm going to put a little asterisk up here. We need to graph their horizontal. All exponentials have at least one, for us, one horizontal asymptote. Okay, they have a horizontal asymptote. Now, the parent horizontal asymptote is at the x-axis. Okay, so the parent, let's just write I like to graph by transformations. Y'all can graph, I mean, you can graph by plotting points if you want to, but I'm going to graph by transformations. So let me shrink this just a little bit. All right. So the parent is basically this with all the transformations taken off. So the parent is y equals 2 to the x. That's the parent. And so for parent points, I like to do -1, 0, 1. That's like my favorite. And so I plug in 2 to the -1 is 1/2, 2 to the 0 is 1, and 2 to the 1 is 2. Okay, those are my parent points. But I'm going to do I'm going to transform. The transformation is down 3, right? -3. That's not up with the x, it's down 3. So I'm going to transform my points so that the y values have subtracted 3. The x values stay the same. So I've got 1/2 minus 3. 1 minus 3 is -2. 2 minus 3 is -1. That's what I got. Now let's talk about the asymptote. The parent asymptote. And what I'm going to do is I'm going to draw the parent asymptote, then I'm going to move it. Okay, here's the parent asymptote right here. Parent asymptote is at the x-axis. Now, my whole graph has been moved down 3. So that means that my asymptote is also going to be moved down 3. Okay, that's the way they work. That's the way the transformations work. If you have an exponential that has an up-down transformation, it's going to move the asymptote. Okay, so now let's graph our points. So I've got -1, let's see, 1/2 minus 3 is what, like -2.5? So -1, like -2.5. Then I've got 0, -2. Then I've got 1, -1. And this is what a regular looking exponential graph should look like. It should skate along its horizontal asymptote, and then it should rise relatively quickly. All right.